In our last lecture, we introduced the surface integral in higher dimensional space. In Rn, surface in Rn, surface integral for continuous function defined over a surface in Rn. Of course, the definition of the surface integral required n-1 dimensional change of variable formula for multiple integral. And our idea to prove the change of variable formula is by mathematical induction. The formula is true for one-dimensional integral. Then we assume that it is true for n-1 dimensional. Therefore, we can use the n-1 dimensional change of variable formula to define the surface integral of a continuous function defined on a hypersurface in Rn. Then with the surface integral, we can prove the divergence theorem, and we have done this last time. Then we will use the change of a variable. We will use the divergence theorem to prove the n-dimensional change of variable formula, therefore completing the mathematical induction. And this ensures that the change of a variable formula is true in every dimensions. And of course, the definition of surface integral is also valid in every dimensions. Okay. Now we have already established the divergence theorem. Now we will use the divergence theorem to prove the n-dimensional change of variable formula. We consider a special domain, a Jordan domain, omega in Rn is simple. We call it simple. Single. Sorry, not simple. Single. If there is a region U in Rn-1 and a parametric surface X from U to Rn such that the boundary of omega is the image of the parametric surface X. Note that as a region U is opened. Okay, region is a Jordan open Jordan domain. So U is opened, but the X is defined on U. In our this definition, X is defined on U, but we require the boundary of omega to be the image of the closure of U, that is including its boundary. But our X is only defined on U. How to explain the image of the closure of U? Okay, here is the explanation. U is opened, that's right, and the X mapped to Rn, the image. But as a parametric surface, the derivative of X is bounded by definition. Therefore, X itself is uniformly continuous in the region U. So it can be continuously extended to the boundary of U. Therefore, this X, although it is only defined on U, but actually it can the domain of definition of X can be enlarged to including the boundary of omega. Therefore, X can also be considered as defined over the boundary of omega. Therefore, this makes the image of the closure of U valid. Okay. Here we use the uniformly continuity of X. The uniformly continuity comes from the assumption that the derivative of X are bounded functions. So this is the single domain, the domain Jordan domain single. So in this case, we also call this X a parametrization of the boundary of omega. X is called a parametrization of the boundary of omega. Okay, so this is a single domain. In other words, single domain is that the boundary of the domain can be covered by a single surface. Okay, for example, the cylinder or cube, the cube is not a single domain, because for a cube, the boundary consists of 6 square. Okay, therefore it is not a single domain, because you cannot find a continuously differentiable parametric surface whose image is the union of all these 6 squares. That is the boundary of a cube. But the balls are single. The balls are single. Here is an example. Balls is single. For example, for the case 3-dimensional case, for 3-dimensional case, our 3-dimensional ball, we can use the spherical coordinates. We choose u. For 3-dimensional case, we choose u to be the 0 pi cos 0 to pi, and x u to r3 x phi theta is sine phi cosine theta, sine phi sine theta, and then cosine phi. Then the image of u, of course this could not be the boundary of the ball, 3-dimensional ball. Okay, because maybe this red half circle does not contain in the image of x, but the closure is the, for the closure of u, that is the closed rectangle, is the boundary of the ball. Here is u. Here is u. The boundary is mapped to the missing half circle in the image of xu. So the image of xu is not the sphere, but the image of the closure of u is precisely the sphere. So the balls is single in 3 dimensions. In higher dimension, you can also prove that for every n, for every dimension n, all these balls are singles. Okay. For single domain, it is easy to prove the change of variable formula. So this is our main theorem. Let omega be a closed single domain. Single domain is the concept we just introduced. That is the boundary of the domain is a single parametric surface. It's almost a single surface. Okay. So this is the single domain, and which parametrization. That is x u to Rn, and D is also a closed domain in Rn, closed Jordan domain. And phi is a map from omega to D. Phi is a map from omega to D, which is C2. We need twice differentiable, such that the map defined by the composition of phi and x, that is a map from U to Rn, of course, is a parametrization of the boundary of D. Okay, this is our requirement for the map, that is the change of variable map in the change of a variable formula. And f is a continuous function defined over D. C1. We need f to be C1. Then we have the integral of f over D equals the integral of f over omega. Then the Jacobian determinant. So this is the change of a variable formula, and the Jacobian determinant does not enclosed by a is not enclosed by a absolute value. So we need a positive or negative sign in front of this integral. The signs for some map phi, you take positive sign. For the other map phi, you need to take a negative sign. Okay. If the Jacobian determinant does not change sign in omega, if the Jacobian determinant does not change sign, then this formula can be written by the usual form. You simply take f to be the constant function. Because as I said, the sign does not depend on the function f. So you take the f to be the constant function 1. Then the integral will be the volume of D, that is positive. So the positive or negative sign must also make the integral on the right hand side to be positive. Okay, but the Jacobian, that is to say the because f is 1, therefore f phi x is also 1. This should be positive. But since the Jacobian determinant does not change sign, so this is this implies that this is exactly the absolute value. Okay, so the positive negative sign can be absorbed into the integrand of the right hand side integral, which absolute value. Okay, but this is only true for the case that the Jacobian determinant does not change sign. If the Jacobian determinant does change sign, sometimes it is positive, sometimes it is negative. So you cannot absorb the sign in front of the right hand side integral into the inside the integral signs. Okay, but of course for the change of a variable, the Jacobian determinant never changes sign. Okay, because it is never 0. So if it changes sign, it could not. If the domain is connected, this is impossible. Okay, but in this theorem, we have not required the map phi to be a change of variable. For this map phi, we only require that its composition, which the parametrization of the boundary of omega is a parametrization of the boundary of D. Okay, so this is omega, this is D. For this map phi, we only require that this phi is carry a parametrization of omega into a parametrization of the boundary of D. Our requirement for this map, for this change of variable map, we don't require it to be one-to-one. We have not required it to be one-to-one. We also have not required it to be so-called diffeomorphism. We only require that if X is a parametrization of the boundary of omega, then the composition which phi gives you a parametrization of the boundary of D. This is the only requirement for our integral formula to be true. This is the only requirement. This is very important. From this result, we can obtain the Balaval-Fitch-Poland theorem. So as a corollary,